pause the video. Where is a function undefined? Well, if you have a fraction, it's where the denominator is equal to 0. If you have a square root, it's where what's under the square root has to be greater than or equal to 0. And if you have a log or ln, what's next to it has to be greater than 0. So this stuff here has to be greater than 0. So our first example, what would make this value undefined is if x is equal to 0, because you just set the denominator equal to 0. Example 2, what would make that equal to 0? Well, you set the denominator equal to 0. So that would be x squared equals 1. So it would be x equals plus or minus 1. And for example 3, where is the square root equal to 0? You set what's underneath the square root must be greater than or equal to 0. So 3x greater than or equal to 2, x is greater than or equal to 2/3. So that is the domain. So where would it be undefined would be when, so it's undefined when x is less than 2/3. Okay, extrema on an interval. So extrema are mins and maxes. So extreme value theorem says if f of x is continuous on a closed interval, so those are our two hypotheses, then our conclusion is that the function will have a maximum and a minimum on that interval. So when we look at these next examples, so you can see on our first example that there is no min or max. And why is that? Is because it's not continuous. On the interval from A to B. Example 2, that does not have a min or a max. And why is that not contradict the theorem is because there's no closed interval. Example 3, so we're looking at from A to B, and you can see that on that interval there is a maximum and there is a minimum. Actually, this is higher, so that is not going to be my maximum here. My maximum's actually over here. So this graph has a min and a max, and that's because it's continuous on the closed interval from A to B. The last example, this is an open circle here. So this graph does have a maximum right there, but there's no minimum. And again, there is a closed interval, but it's not continuous. So that's why it doesn't contradict the theorem. Okay, relative or local extrema, so relative local mins or maxes can occur in a local area. So it's not necessarily the maximum or the minimum, they're just relative max or mins. And they can occur at hills or valleys that have horizontal tangents. And remember, a horizontal tangent is when the derivative is equal to 0, or at sharp points. And if you remember, at sharp points, that's where the derivative is undefined. So when you look at this picture here, I have a horizontal tangent right there, and that is a relative max. I have a horizontal tangent here, and that's another relative max. I have a horizontal tangent here, and that's a relative min. I have a sharp turn right here, and that is actually it's a relative, actually in this case, it would be an absolute min. And again, these relative mins, the derivative is equal to 0 because of that horizontal tangents. And up at these two, the derivative is equal to 0 because they're horizontal tangents. At the endpoints, you can have absolute extrema. So this endpoint has an absolute max, because that's the highest point of the graph. This can also be considered a relative min, but in this case, it's also the absolute min. So again, what I just showed you, how can we relate these local extrema to derivatives, is hills or valleys are where the derivative is equal to 0, and sharp turns are where the derivative is undefined. Critical values are where the derivative is equal to 0 or where the derivative is undefined. If that happens, then C is considered a critical value. That is different than a critical point, because a critical point means there's an actual point on the graph. So if F is defined at C, then you have a critical point. But if there's an asymptote or a hole, which makes the derivative undefined, then that would just be a critical value and not a critical point. Relative extrema can only occur at critical numbers. So again, critical numbers are where the derivative is 0 or undefined, but not every critical value is an extrema point. Absolute extrema, so that's absolute mins and maxes, can occur at critical values or at an endpoint on the interval. And sometimes this notation you'll see where f of c, so that is a y value, is less than or equal to the entire function. So that would create a minimum at f of c. If f of c, so that's another y value, is greater than or equal to the function, then that would create a maximum. Sometimes this notation is shown in multiple choice questions. Okay, so this next graph, we're going to find all the critical values. So again, critical values, f derivative is equal to 0 or f derivative is undefined. Relative extrema and absolute extrema. So I'm going to do derivative equaling 0 first. So right here is a critical value. Here is another horizontal tangent, so that's another critical value. There is another horizontal tangent, so a critical value right there. Another horizontal tangent, so right there is a critical value. There are no sharp turns, but on this graph, there is a undefined, so this is also considered a critical value. Relative extrema, so up here is going to be a relative max. This is neither a relative min nor a relative max. I won't put anything there. This is a relative min. And actually, since this does not have an arrow at the end, we can also say that this is an absolute min. This critical value is neither a min or a max. And this critical value here is a relative min. And again, this graph has no maximum because the function is not continuous on a closed interval. So that's the extreme value theorem. Because we have this asymptote here, it doesn't guarantee a min or a max. All right, the next part of notes, we are going to find absolute or global extrema. So that's absolute mins and maxes. So step one is find the critical numbers. That's your derivative equals 0. Derivative is undefined. You determine the endpoints of the interval. That's usually given. You set up a table that uses the endpoints and the critical values as the x values. Then you evaluate them in the original function. And then you determine the min or max by looking at the y values, the biggest and smallest numbers. Okay, so we are going to find absolute extrema. So again, this is a polynomial function. So that means that the domain is all real numbers. So that means that this graph is continuous. And we have a closed interval. So that extreme value theorem guarantees a min and a max. Okay, so our process, step one is we're going to find our critical values. So we're going to find where is the derivative equal to 0. So first we have to find the derivative, which would be 12x cubed minus 12x squared. We're going to set that equal to 0. So I'm going to factor. And I get x equals 0 and x equals 1. Where is the function undefined? Is nowhere. And my next step is I'm going to make a table. Whoops. So I put my endpoints, and then I put my critical values, which is 0 and 1. And then I'm going to take and I'm going to plug them into the original function. When I plug in -1, that's going to give me 3 plus 4, so 7. When I plug in 0, I get 0. So again, I'm plugging it into this function right here. When I plug in 1, I get 3 minus 4, which is -1. And when I plug in 2, I get 16. So my absolute minimum is the smallest of this, which is -1. And that happens at x equals 1. And then my absolute maximum is the biggest number, which is 16. And that happens at x equals 2. All right. If you want to pause and try the next examples on your own, you can, and then come back and check your answers. So how these problems get harder is finding the derivatives are a little bit harder. So when I find the derivative of g, I'm going to have to do quotient rule. So I'm going to do low d high minus high d low all over low low. So that's going to simplify to 6t over So we're going to find where is the derivative equal to 0. And when you have a fraction, that's where your numerator is equal to 0. So I'm just going to set the numerator equal to 0, and I get t equals 0. Where is g prime undefined? A fraction's undefined when the denominator equals 0. So I'm going to take the denominator and set it equal to 0. Well, that's never going to happen because t squared can never equal -3. So there is none. And then the next step is that table. So we're going to make a table, but this time it's not x, it's t. And we have g of t. So again, our interval, I should have mentioned this, the denominator is never equal to 0. So this function is continuous on this interval. So there will be a min and a max. So I have my endpoints of -1 and 1, and then my other critical value of 0. And remember, I'm plugging into the original function because I'm trying to find mins and maxes on the original function. So when I plug in -1, I get 1 over 1 plus 3, so 1/4. When I plug in 0, I get 0 over 3, which is 0. When I plug in 1, I get 1/4 again. So these both are considered maximums, and then the 0 would be your minimum. So my absolute max is 1/4, and that happens at t equals plus or minus 1. And then my absolute min is 0, and that happens at t equals 0. And pay attention, if they want the ordered pairs, you would give them the ordered pairs. If they just ask for the maximum, that is the y value. And if they ask where it happens, that's the x value. Okay, example 3. We have cosecant. So remember, if I rewrite cosecant, that's really 1 over sine. So where is sine equal to 0 is when x is 0, pi, 2 pi, and so on. But on this interval, none of those values occur. So this function is continuous, so there will be a min or a max. So I'm going to find the critical values. So my critical values are where f prime is equal to 0. So I'm going to go back to cosecant. Find the derivative of cosecant is negative cosecant x cotangent x. And I want to know where that is equal to 0. So to solve this, I'm going to rewrite this. So I'm going to change this to negative 1 over sine x times cosine x over sine x. So that's really negative cosine x over sine squared x. And so where is a fraction equal to 0 is where the numerator is equal to 0. So I'm just going to look at where is cosine equal to 0. Sorry, where is negative cosine equal to 0? So that would be at pi over 2, 3 pi over 2, and so on. But on this interval here, there are none. And then where is the function undefined? I'm going to go back to this derivative here, and that would be where the denominator is equal to 0. So that's looking where is sine equal to 0, which we already solved up here. And that's 0, pi, 2 pi, and so on. And again, in this interval, that's none. So when we make our table, the only thing we have on our table are the endpoints of pi over 6 and pi over 3, because none of our critical values, remember these were our critical values and these are our critical values, none of them fall in that interval. So now we're just going to be looking at pi over 6. So I'm going to go to 1 over sine. So sine of pi over 6 is 1/2. So the reciprocal of that would be 2. Sine of pi over 3 is square root of 3 over 2. So the reciprocal of that would be 2 over square root 3. So my absolute max is 2, and that happens at x equals pi over 6. And my absolute min is 2 divided by the square root of 3, and that happens at x equals pi over 3. Okay, so I would like for you to try the last example, pause the video, and then come back and see if you get the right answer. All right, cube root of x is continuous, and it's continuous on that over all real numbers. So there will be a min or a max. So I'm going to find g prime of x. So this is really x to the 1/3. So when I find the derivative, it's 1/3 x to the negative 2/3, which I can simplify to 1/3x to the 2/3. So I want to find where is the derivative equal to 0. Well, when I have a fraction, that would be where the numerator is equal to 0, and you can't turn 1 into 0, so this means there will be no horizontal tangents. Then I want to look where the derivative is undefined, and that's where the denominator is equal to 0. So that will happen at x equals 0. So I just like to think about this graph here, the cube root of x. So there are no horizontal tangents and the derivative is undefined at 0. So since the original function is continuous, what's happening at 0 would be a sharp turn, because we can plug in 0 into the original function, because g of 0 is just the cube root of 0, which is 0. So there is a point, and what's happening there is a sharp turn. That's just a side note. Okay, so then our next step is making a table. So we have our x values and then our function. We put our endpoints and our critical value of 0. And then remember, we're plugging into the original function. So you're plugging into the cube root of x. So the cube root of -1 is -1. The cube root of 0 is 0. The cube root of 8 is 2. So this is going to be my max, and that is going to be my min. So the absolute max is 2, and that happens at x equals 8. My absolute min is -1, and that happens at x equals -1. And that is it for notes.